Dear friends, Maths Aspirants is a collective of mathematics students, research scholars, faculty members across India, initiated by myself in 2017. And we used to organize several online programs to help the students who prepare for different national level competitive examinations. As a part of that series, today we have a session on group theory, and we are blessed to have Mr. Adithya, a research scholar from ISI Delhi, to handle this session. Mr. Adithya studied his MSc from ISET Trivandrum and currently in the second year of PhD at ISI Delhi. And his broad research area is algebraic number theory. So today he will discuss previous year questions from group theory of question papers of IIT, JAM, GATE, NET, TIFR, GS exams. I'm sure that today's session will be really beneficial for those who are seriously preparing for these exams. I welcome everyone to this program. I would like to express my sincere gratitude and thanks to Mr. Adithya for accepting our invitation and joining with us. Welcome, Adithya.
Thank you, sir. First of all, I'd like to thank you for giving me this opportunity. Anyways, so I have collected some questions from previous year JAM, GATE, TFR, GS, and also the ISI entrance exams. So the questions are of varying difficulty levels, and I have tried to assort them in such a way that we can cover it topic wise. So if at any point you'd like to ask something, kindly ask it, or you can type it in the chat box. So yeah, you can raise your hands as well. I will try to take it. Anyways, so yeah. So we'll be starting with some problems based on basic, I wouldn't say basic, but like from the fundamentals of group theory. So this is the first question. I wanted to start it off with something which might be easier. So this is a question from TFR GS exam. So the question is, what is the number of even positive integers n such that every group of order n is abelian? So, I mean, I would be happy if someone can write the answer in the chat box for this question, and then I'll see how to go about it. This is my first time, so please please feel free to give feedback. Anyways, so number of even positive integers n such that every group of order n is abelian. So what is the first thing we know about abelian groups? This is something which we learn right at the start, which is that if the order of the group is less than or equal to 5, then G is abelian. So this is one of the theorems which we learned early on in group theory. So this already gives us two even positive integers, which is 2, 4. And now we are looking at even integers n greater than equal to 6 and even. So in this case, we read about the dihedral groups, which is either denoted by dn or d. Okay, if I take n equals 2m, then it's either denoted by d2m, which is n, or dm, which is the dihedral group. And we know that for m greater than equal to 3, dm is non-abelian. The two generators of DM, which is the X and Y, where X has order M, Y has order 2, they don't commute. So for every even integer greater than equal to 6, we have a non-abelian group. So the number of even positive integers n such that every group is abelian are only 2 and 4. Hence the answer is B, which is 2. I see some people have answered in the chat. So, so anyways, let's move on to the next question. So this is about computing the order of an element in the product of groups. So this is a question from the ISA entrance exam. So we have the group G, which Z6 here is integers modulo 6. So Zn is integer modulo n. It's either denoted by Z subscript n or Z mod nz. The notations keep varying. So yeah. So we have Z6 cross Z15 cross Z20. It's a G is a product of 3 groups. And we are asked to compute the order of an element 1, 2, 3. So in general, when we have G and H are finite groups, X belongs to G, Y belongs to H. The order of X comma Y in G cross H is basically LCM of order of X in G and the order of Y in H. So this you can also extend for any finite product of groups. So in our case, order of the element 1, 2, 3 would be LCM of order of 1 in G in Z6, order of 2 in Z15, and order of 3 in Z20. So order of 1 in, so anyways, if we take any A in Zn, what's the order of A in the group Z mod nz? This is given by n divided by GCD of n comma A. So 1 always generates the entire group Zn. Zn is a cyclic group with generator 1. So order of 1 in Z6 would be 6. Order of 2 in Z15 would be 15 divided by GCD of 2, 15. GCD of 2 and 15 is 1. So this would be 15. And order of 3 in Z20 would be 20 divided by GCD of 3 and 20. GCD of 3 and 20 is again 1. So this would be 20. So basically, we get this is basically LCM of 6, 15, 20. So now the LCM of 6, 15, and 20 is actually 60. So the order of this element would be 60. So the answer is C. So I hope everyone's okay with this. Are there any doubts up until now? Pete,
No,
please feel
sir.
free.
Okay.
Please feel
Okay,
free
okay,
to
sir.
raise your hands. Yes. Okay. Yes. Any questions? So this is how we compute the order of an element in the product of finite groups in general. Okay. So let's move on to this question. Let G be a group of order 10 and X0 is an element of order 2 in G. So now we are given this set X, which is basically the set of all X in G such that X cube is equal to X0. So we are basically asked to find the cardinality of X. So with the given information, how can we work this problem out? So let's start. So we have X naught is not identity because it has order 2 and X naught square is identity. Right. We have order of G is 10. So now suppose let X belong to X, which means X cube is equal to X naught. Sorry, X naught. So substitute this here. This implies X cube the whole square is equal to X naught square, which is identity. And what is this? This X plus 6 equals identity. So from here, what do we get? We get that order of X divides 6, which means order of X equals 1, 2, 3, or 6. These are the four possibilities we have for the order. Right? So now also order of X must divide 10, which is the order of the group. This is due to Lagrange's theorem, which we all might know. So from these two, we get that order of X can be either 1 or order of X is 2 because 3 and 6 don't divide 10. Okay. So first, order of X equals 1. What does this give us? Which is the element of the group which has the order 1? It's the identity element. So we get X is identity. Right. So this implies X naught, which is X cube, is also identity. But we have that X naught is not identity. So this is not possible. So what about the other case? Order of X equals 2. So we have X square is identity. Now what is X naught? It is X cube, which can be written as X square times X. And X square is identity, so this becomes X. So we get that X is actually equal to X naught. So we have now tested all the possible cases, which imply, so X belongs to X implies X equals X naught, which gives us X is basically the case at singleton X naught. So which means X has one element. So is everyone okay with this?
Yes, sir.
Yeah. Okay. So let's move on to another interesting question. Let Z100, it's the group of integers modulo 100 with respect to addition. So now the question is, how many subgroups does this group Z mod 100Z or Z100 have which do not contain the element 10 or 10 bar, if you are looking at however you write the terms. So this is again a question from the ISI entrance exam for MMath. So let's try to work this out. So Z mod 100Z or Z100, what do you know about this? It's cyclic group of order 100 and it has another property for all D dividing 100, for all the divisors of 100, there exists a unique, the exclamation stands for unique. There exists a unique subgroup G of Z100 with order D. And G is basically the cyclic group generated by 100 by D in Z mod 100Z. You can actually look at this. So if you take D equals 2, you get the subgroup G to be 0, 50. 50 is 100 by 2 and it has order 2. So this would be the subgroup of order 2. And now here we already have that this doesn't contain 10. So we first need to find out all the divisors of order of G. Order of G is 100 is basically 2 square times 5 square, right? So the total number of devices. So number of devices would be. So the formula for number of devices for any n, once you write its prime factorization, p1 power e1 to pr power er. So you just collect all the exponents e1 to er. So if you have n equals p1 e1 so on up to pr er, then number of devices is basically e1 plus 1 times e2 plus 1 dot up to er plus 1. So this is the general formula. So using that, here we get 2 plus 1 into 2 plus 1 is basically 3 times 3, 9. And the devices, you can actually write it down. It's 1, 2, 4, 5, 10, 20, 25, 50, 100. So these are the 9 devices of 100. So now what are the subgroups? So the subgroup of order 1 would be this, the identity. Subgroup of order 2, as we saw before, is 0, 50. And subgroup of order 4 would be the group generated by 25, which is 100 by 4. Similarly, this would be 20. This would be 10. This would be the group generated by 5. This would be the subgroup generated by 4. This would be the subgroup generated by 2. And this is basically the entire Z100. So now this contains 10. Z100 contains 10, of course, because it's the entire group. So now consider the group subgroup generated by 2. Will 10 be a part of this group, this subgroup? That depends if 10 comes in the 10 is a multiple of the generator, mod 100. And 2 times 5 is 10. So 10 will definitely appear in this group. What about 4? The subgroup generated by 4. So subgroup generated by 4 in Z mod 100Z would be 0, 4, 8, 12, so on up to 96. Right? It's basically multiples of 4. And 10 is not a multiple of 4. So this won't contain 10. So similarly, if you look, 5 will contain 10, 10 will contain 10, 20 won't contain, the subgroup generated by 20, the subgroup generated by 25 won't contain, the subgroup of order 2 doesn't contain because it is 0, 50. And the subgroup of order 1 is the trivial subgroup which doesn't contain 10. So the number of subgroups which doesn't contain 10 is 1, 2, 3, 4, 5. So how many subgroups does not contain 10? The answer is 5. So whenever questions like counting comes, it's very important for us to look at the trivial subgroups. We might miss counting them. So it's always important for us to count the trivial subgroups. So remember that always. Anyways, let's move on to the next question. I hope there wasn't any doubts in this. I mean, if you have any doubt at any point, kindly raise your hands. I'll ask. Yeah. So moving on. So this is the next question. So now similar to Zn, for every n in n, we can have this group Un, which is basically the set of all x bar in Zn such that the GCD is 1. GCD of x and n is 1. And this forms a group under multiplication modulo n. So now the question is, which of the following is or are true? So there could be multiple statements which are true. Anyways, so U of n. So we have smaller numbers here. So we can directly try to compute. U of 8. U of 8 would basically be 1 bar, 3 bar, 5 bar, 7 bar. Right. So now this is a group of order 4. So this would be cyclic if we are able to find an element of order 4. So now we'll check if any of these elements have order 4. So now 3 bar square is basically 9 bar, which is 1 bar. And the identity of this group is 1 bar. So this is Z. So 3 has order 2. 5 bar square is 25 bar. 25 is again congruent to 1 mod 8 because 25 minus 1 is 24. So this is again of order 2. What about 7 bar? 7 bar square is 49 bar, which again 1 bar because 49 minus 1 is 48, which is divisible by 8. And this is again identity. So apart from 1, which is the identity, every non-identity element has order 2. So this is basically isomorphic to Z2 cross Z2, if you want to look it like that, or what is called the Hleng-4 group. This is not cyclic. So what about U5? 5 is a prime number, right? So every non-zero element of Zn would be a part of Un. So you'll have 1 bar, 2 bar, 3 bar, 4 bar. So now we'll check again if there's any element of order 4. So 2 bar square is 4 bar. 2 bar cube is 8 bar, which is 3 bar. And 2 bar power 4 is 16 bar, which is 1 bar. These are modulo 5. So 8 is congruent to 3 mod 5 and 16 is 1 mod 5. So we get that 2 has order 4. And if you could see, it did generate 3, 4 and 1. So U5 is cyclic. Similarly, we can check for U12 and U9. So U12 would have 4 elements, 1 bar, 5 bar, 7 bar, 11 bar. And now 5 bar square is 25, which is again 1 mod 12 because 25 minus 1 is 24, which is divisible by 12. 7 bar square is 49, which is again congruent to 1 because 48 is divisible by 12. And 11 bar square is 121, which is again 1 because 121 minus 1 is 120, which is 12 times 10. So U12 is also the Hleng-4 group or Z2 cross Z2, which means it's not cyclic. Now the final group D we have is U. D is U of 9, which is basically 1 bar, 2 bar, 4 bar, 5 bar, 7 bar and 8 bar. So this is a group of order 6. So we need to see if we can find an element of order 6. So again we can start with 2. So 2 bar square is 4 bar, 2 bar cube is 8 bar, 2 bar power 4 is 16, which is 7 bar, 2 bar power 5 is 5 bar, I guess, because 2 bar 5 is 32, so 32 minus 5 is 27, and 2 bar power 6 is 64, which is 1 bar, because 64 minus 1 is 63, which is 7 times 9. So 2 indeed has order 6. So we get that U of 9 is cyclic and U of 12 is not cyclic. So the correct options are B and D. So now I'd like to save time for you all here, and this could be used in the exam. You can remember this if you want, which is called the primitive root theorem. I won't get into the proofs anyways. So U of n is cyclic if and only if n equals 1 to 4 p power e or 2 times p power e, where p is an odd prime and e is greater than equal to 1. So this is an important theorem which saves a lot of time whenever we are checking questions such as this. This is called the primitive root theorem. So p is an odd prime. So the only powers of 2 for which un is cyclic is basically n equals 1 to 4. And then for any odd prime p, it should be of the form either p power e or 2 times p power e. It's called the primitive root theorem because a generator of un is called a primitive root mod n. And yeah, so it's something which combines both number theory and algebra. So now going back to our question, U8 is definitely not cyclic by our theorem. 5 is an odd prime, so U5 is cyclic. U12 is 2 times 6. It's not of the any form. It's not of the form p power e or 2 times p power e because it's 2 times 6 and 6 is not a prime part. So 12 is not cyclic and 9 is cyclic because 9 is 3. U of 9 is 3. So 9 is 3 square, so U of 9 is cyclic. So I hope this is a nice small theorem which could help you. So the next question is also related to U of n. So let's go for it. So U of n is again defined here. Then which of the following statements is true? U of 5 is isomorphic to U of 8, 10 and 12, 8 and 10, 8 and 12. So we can use the primitive root theorem here to get what we want. So basically here what we have are U of 5, U of 8, U of 10, U of 12. So by our primitive root theorem, U of 5 is cyclic, U of 8 is not cyclic, U of 10 is cyclic because 10 is 2 times 5, and U of 12 is not cyclic. So now let's look at the options. U of 5 and U of 8. U of 5 is cyclic, but U of 8 is not cyclic. So they are not isomorphic. 10 and 12. U of 10 is cyclic, but U of 12 is not cyclic. Again, they are not isomorphic. 8 and 10. U of 8 is not cyclic, but U of 10 is cyclic. So they are not isomorphic. U of 8 and U of 12. Just because they are not cyclic doesn't mean they are isomorphic. So order of U of 8, but now we can conclude that this is true because all our other 3 options are false. But we have U of 8 as order 4 and U of 12 as order 4. And U of 8 is not cyclic, which means U of 8 is isomorphic to the Hlm-4 group, which can be written as Z2 cross Z2. And since U of 12 is also not cyclic, it just can be written as Z2 cross Z2. So they are indeed isomorphic. So are there any questions till now?
No, sir.
Okay. Yeah, thank you. So we'll again continue with, this is a gate question. It's a numerical answer type question. Let G be a group with identity element E. G and H are elements of G such that the following holds. G not equal to identity, G square equals identity, which means G has order 2. And H is not identity, H square is not identity, and GH G inverse is H square. So now the question asks the least positive integer n such that H power n is identity. So it's basically asking us to compute the order of H. So the one crucial thing which we will play with here is GH G inverse is H square. So now what can we do with this? See, whenever we look at GH G inverse, the conjugation kind of an operation, we think of two possibilities to go. One is g h power n g inverse, which is basically g h g inverse the whole power n. Or you can think of something like g power n h g power n inverse is basically g power n h g power minus n. And we know that g and g inverse always have the same order. So in our case, the second one helps because we know the order of g and not order of h. Right. So we'll try to compute what is this. So g square h g power minus 2, basically g square inverse. So this is basically h. Because g square is identity and this is also identity. So this is basically e h e, which is h. Right? What's the other way we can go about it? G square h g square inverse. And let it as g. So g square inverse is same as g inverse square. So this you can write as g times h times g inverse. So you can make this g inverse times g inverse, which gives you g h square g inverse. Because g inverse is h square. Now you know g h square g inverse is g inverse the whole square. The first property I have written. So now again g inverse is h square. So this is basically h power 4. So one equation we had was g square h g square inverse is h and g square h g square inverse is h to the 4. Combine this. This implies h equals h to the 4 and you multiply by h inverse on both sides, you get h cube as identity. So h cube is identity, which means order of h divides 3. This implies order of h can be 1 or order of h equals 3. Now we are given h is not equal to identity. So order of h cannot be 1. So you get order of h is 3. So the answer is 3. So whenever we look at conjugation problems like this, we try to work with these two properties. These two properties are what we tend to use whenever we work with conjugation. So is this okay? Okay, so let's move on to another interesting question. This is from the ISI M-Math exam. So let G be a cyclic group and A and B are elements of G. Suppose there does not exist any x in G such that x square is A. So for any x in G, x square is not equal to A. And similarly for any y in G, y square is not equal to B. So we are asked for AB. Now can AB have an element G such that G square is AB? Or will it have G cube equals AB? Or the smallest exponent possible, so like that, is 4, or none of the above is true. So we have, so let's go with each term one by one. So first thing we have is G is cyclic. So let G be generated by G. Right? This is the first thing we have. What's the next thing we have? A and B are equal to G. A and B are in G, sorry. So A comma B in G implies A equals G power I, B equals G power J for some Ij in N. Right? So we
Sir,
have this.
please repeat this line. I have not got it.
Yeah. So G is a cyclic group generated by the element small g, which means every element can be written in terms of that, right? Like when we say Z mod NZ, okay, so whenever we try to use G, we are just given G and not the operation. We usually write it in terms of pass. Only when we know that it's like an additive group structure, we tend to use the IGJG kind of structures. Like for example, okay, let me take an example here. So whenever you take something like Zn as the group, we say Zn is generated by the element 1, which means every element A bar in Zn can be written as A bar equals 1 bar plus 1 bar plus 1 bar plus dot dot dot. Right? So this 1 bar generates the entire group Zn. Right? So in this case, we write it as A times 1 bar. Right?
Yes, sir.
So in general, we write it as powers. Like, so this G power I basically is like G star dot 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 star G I times. Right. So G is basically generated by G implies you have E, G, G star G, and so on up to some finite times. Since we aren't given finite, so it can keep going. So instead of writing star, we just write it as G power I. So that's just notation. Anyways, so now we have this. So now we have just dissected the information given for us in the first line. So now let's look at this in this part. Suppose there does not exist any x such that x square equals a. So which means for all x in G, x square is not equal to a. So what can we get from here? So you take any x in G, x can be written of the form g power k for some k. And x square is not equal to a implies g to the 2k is not equal to g to the I, which means the power I is not even. The power I is basically odd.
Yes, sir.
And this is true for all k. And that's why we are able to conclude I is odd. Right?
Yes,
Or
sir.
otherwise, if you are not able to wrap head around this thing, let's look at the other way around. Suppose I is even, which implies I can be written as 2 times, let's say, some I prime. This implies A can be written as g power 2 I prime, which is basically g power I prime, the whole square. So A can be written as square of an element. Right? So if I is even, A can be written as square of an element. So if A cannot be written as square of any element, which means I is odd. So is this clear?
Yes, sir. Clear.
Okay. So we get that I is odd. And similarly, J is odd. Alright? Because we are given there exists no y such that y square is b. B is not square of any element in G. So J is also odd. So now what can we say about AB? AB is basically G power I times G power J, which is basically G power I plus J. So now I is odd, J is odd, implies I plus J is even. And let I plus J be equal to 2 times K for some natural number K. And this is basically G power 2K. And this can be written as G power K the whole square. So let, if I take H to be G power K, we have H square is AB. Which means AB can be written as square of an element. Which is what option A says. Okay. So there might be a little bit confusion here because the options give G. So yeah. So yeah. So we have that there is an element G such that G square is AB, and that G square is basically X power K, where X is the generator of G and K is I plus J by 2, where I is the exponent of A and J is the exponent of B. So I hope this question, I hope this was okay. This wasn't very difficult. So I move on to the next question. So now this is a true or false question from TFR exam. Let G be a group generated by two elements X and Y each of order 2, then G is finite. The answer is actually false because see, when X and Y are elements of finite order, and xy equals yx, whenever they commute, that's when G, which is the group generated by X and Y, is finite. Yeah. When they don't commute, we won't have an element of, we won't have a group of finite order. I don't have an example right at the top of my head. I will try to find an example, write it, and let you all know. But the answer is false.
Sir, one thing, I have not seen this question before and not known also. But what is the, how can I guess it would be false or something? It may possible sometimes it is not immediately possible for write down proof or
Yeah,
making counter
that's true.
example.
That's
But
true.
what?
Writing, solving a question completely during exam, during a competitive exam is difficult. So at that point, we just have to guess sometimes. So look at this question. Let G be a group of elements, group generated by two elements X and Y, each of order 2. Then G is finite. Your first instinct might be it's true because both elements are finite order. And so if the group is generated by them, it must be finite.
Finite, yes, yes.
Right. So that's the first
Hmm,
instinct which comes to our mind.
yes.
But the thing is, we always look, whenever we are generating a group of two elements, say X and Y, we always have to look at the element xy. So we know this that, this is quite an example which is given most of the times. We always know that if x and y are elements of finite order, xy need not be an element of finite order. And the example always given is in terms of matrices. So there is this theorem which we always prove in group theory. X and y have finite order and x and y commute, which implies xy equals y next, which implies xy has finite order. Right? So this is a theorem which is proven in group theory. If x and y are elements with finite order, and if x and y commute, which means xy equals yx, then xy has finite order. Are you familiar with this
Yes.
theorem?
No, I think I have used in some part of a problem where it is given, but
Yeah.
as a standard
Anyways,
result, I
you can try
did not.
to show this. It's not difficult to prove.
Yes, yes, it is. I am trying to don't
Yeah.
require your proof immediate.
Yeah. So you can try to look at this. So if they commute, then we know it has finite order. And right after this theorem, we are always given an example, because finding counterexamples on spot during exam is all difficult. I agree. So whenever they won't commute. So now, if they commute, we know it has finite order. What if they don't commute? And whenever we think of non-commuting operators, we think of one thing, which is
Matrices or
matrix multiplication. Correct. Right. So there is an example. I think it's SL2Z, is basically the set of all 2 cross 2 matrices with integer entries and determinant 1. This can be generated by 2 elements of finite order, but SL2Z in itself is infinite. So this is a very important example which is always given whenever we do group theory. So that same example might work here, will work here, I'm pretty sure, but I don't know if I can give generated by elements of order 2, but yeah, you can show that. So basically SL2Z is generated by 2 matrices, which is basically 1 1 0 1 and 0 minus 1 1 0. It is generated by 1 1 0 1 and 0 minus 1 1 0. These 2 matrices. This has infinite order, and you can show that if I take this as T and this as S. T has infinite order and S has finite order. Right. And you can do some combinations of T and S to get another element of finite order, and then you can work it out. That SL2Z will be generated by 2 elements of finite order, but the order of the group is infinite. Right. So the answer is false. So whenever they are asking about this thing, elements of finite order, and they are talking about xy and all those things, order of xy, or even the order of the group generated by xy. One of the important things we need to look at is if x and y commute, which is if xy equals yx. Even when we are asked to compute the order of xy, this is important. Because we know xy has finite order only when x and y commute. So this is a question which depends on if you know examples. And I agree it's always difficult to think of examples when you are in an exam hall. I have personally been in that space and I know how frustrating it is to find an example. So at that point, what I would suggest is don't attempt the question or leave the question for attempting in the end. And first go with questions which you're comfortable with. Okay. So we are already halfway there and I do have quite a lot of questions to go through. Anyways, so this is again this is basically counting group homomorphisms. So now we are done with group theory, the initial part, and now we are entering into homomorphisms and questions related to that. So the first question is the number of group homomorphisms from Z mod 4Z to S4 is equal to how much? So we have the domain to be Z mod 4Z, which is cyclic group generated by 1. So it's enough for us to look at where 1 would be mapped, right? So let sigma be, so let me take f from Z mod 4Z to S4. This is a homomorphism. And let sigma be f of 1. Right? Sigma in S4. So what's the first thing from this we can have? Sigma power 4. It's basically f of 1 bar plus. Okay, so 1 has order 4. So f of 1 bar plus 1 bar plus 1 bar plus 1 bar is basically E, where E is the identity of S4. So this just becomes f of 1 bar the whole power 4. Here I'm writing power 4 because S4 is a group under composition and we usually write it as exponents. Is identity, which means sigma power 4 is identity, which means order of sigma in S4 divides 4, which means order of sigma is 1 or order of sigma is 2 or order of sigma is 4. So now counting the number of homomorphisms from Z mod 4Z to S4 has been reduced to counting the number of elements in in S4 of order 1, 2, and 4. Order of sigma is 1, which means sigma can be only identity. So we get order of sigma equals 1 implies sigma as identity, which gives us 1 homomorphism here. So now order of sigma is 2. So now we need to find out number of elements of order 2 in S4. So how do we usually work with elements of S4? We basically look at the partitions of 4. We have 4, 3 plus 1, 2 plus 1 plus 1, 2 plus 2, and 1 plus 1 plus 1 plus 1. So these are the the 5 partitions of 4. And now what are the orders? Here the order is 4. Here the order is LCM. It's basically the LCM of all the terms in the partition. So here it's LCM of 3, 1, which is 3. LCM of 2, 1, and 1, which is 2. LCM of 2 and 2, which is 2. LCM of 1, which is 1. So this is basically the order. And now next we have number of elements of that cyclic decomposition. So that if we compute, we'll get 6, 8, 6, 3, 1. So how do we compute for 4? It's basically 4 factorial by 4 power 1 times 1 factorial. It's basically 4 factorial by 4, which is 6. Similarly, for 3 plus 1, it would be 4 factorial divided by 3 power 1, 1 power 1 times 1 factorial times 1 factorial, which is basically 4 factorial 24 over 3, which is 8. Similarly, we can compute for all the others. So the number of elements of order 2 in S4 is basically 6 plus 3, which is 9. So we have 9 possible homomorphisms here. So finally, order of sigma equals 4. We need to see the number of elements of order 4 in S4. So number of elements of order 4 in S4 is 6, which means we have 6 homomorphisms here. So total number of homomorphisms is equal to 1 plus 9 plus 6, which is 16. So 16 is the answer. So now let's move on to the next question. I think this is from JAM, but yeah, you can check it out. Let G be an abelian group and phi from G to Z plus is a surjective group homomorphism. Surjective is onto. Onto surjective both imply the same. So Z plus is the group of integers with respect to addition, and G is a group such that there is a surjective group homomorphism from G to Z. So now, since it's surjective, 1 in Z will have a pre-image. So we are taking that to be A. So now let 1 be phi of A for the main G. So now we have two statements. So the first statement is for every G in G, there exists an n in Z such that G A power n belongs to kernel of phi. So now let's check if P is true. So now let G belong to G. So now we need to get some integer n. So given G, how can we go to n? We have an homomorphism from G to Z. So let's just try to see if that would work. And n be equal to phi of G. And this is an integer. So now we need to show C G A power n, if that belongs to kernel of phi. So now, which means I need to check now phi of G A power n. I will use the property of homomorphisms. This is basically phi of G plus phi of A power phi of A plus phi of A so on up to n times. So this would be n times phi of A. So this would just be n plus n. That gives me 2n. So we were somewhat right. So this would be n plus n times 1. So what if we take n to be minus phi of G? So we were somewhat right, but we were wrong. Like this won't work. So we can take and let m be equal to phi of G, which is in Z, and let n be equal to minus m. So now this would give me m plus n times 1 because phi of A, this is basically m plus n, which is 0. So somewhere with some initial guess, which we are able to make based on the given details, we were able to show this. We are able to show that this statement is actually true. This implies G a power n belongs to kernel of phi. So P is actually true. I mean, one more way which someone could have looked at it is we want G a power n to be in the kernel of phi. Right. So now let k be any integer, then phi of G a power k is again phi of G plus k times phi of a, which is basically phi of G plus k. Now you want this to be equal to 0 for some k. Right. So you take k to be minus phi of G. That would give you what you wanted actually. So this is the way we actually prove, but the first way which we did was just heuristic guess on what could we work with. Given the conditions, what can we work with? So now let's look at Q. Let E be the identity of G and let A denote the subgroup generated by A. Then G can be written as product of two groups, which is basically kernel of phi times A to the n. I mean kernel of phi and the subgroup generated by A. And kernel of phi and the subgroup generated by A have trivial intersection. Let's try to prove this. So what does it mean by G equals kernel of phi times ideal generated by A? This is if and only if for all G there exists X in the kernel and N in Z such that G can be written as X a power N. Right. So basically any element of G can be written as a product of any element from kernel of phi and any element from the subgroup generated by A. And that's simply what this statement means. Right. So now we can move on with this. So now let G belongs to G. We know G a power n belongs to kernel of phi for some integer n. How did we get this? We got this from P and we were able to show P is true. Right? So which implies G a power n is equal to X for some Xn kernel. This implies G can be written as X times a power minus n. So we showed what we wanted. This implies G can be written as kernel of phi times the subgroup generated by A. Right? So in fact, P is helping us prove Q. Like the statement P is helping us prove the statement Q. But the statement Q is not done yet. We have one more part to prove, which is this thing. Kernel of phi intersection is trivial. So let's try to show that. So we always know that this containment is true. Because it's not ideal, sorry. Kernel of phi and subgroup generated by A both are subgroups and both contain the identity. So their intersection will of course contain the identity. The other way around is what we need to check. Let X belong to kernel of phi intersection this. X belongs to kernel of phi. This implies phi of X is 0. Right? X belongs to this. This implies it can be written as A power K for some K in Z. Combine these two, we get phi of A power K is 0. This implies K times phi of A, property of homomorphism, is 0. And phi of A is 1. This implies K is 0. This implies X is basically identity, which is A power 0. So this actually shows that kernel of phi intersection A is in fact just identity. So in fact Q is true. Fine. Let's move to the next. Yes. Any questions? Hello.
So someone has raised their hand.
Yeah, that's what I'm not able to hear. So yeah.
I think due to network disturb, or
Yeah.
he should type in the
Okay,
chat.
so
Yeah,
I
Yes,
don't know
yes,
what's the
he has
is there
problem.
typed.
any
He
issue?
has
Okay.
typed.
No, sir, it's just so the problem was basically this thing. So we have G is an abelian group, phi from G to Z plus is surjective group homomorphism. Since it's surjective, one will have a pre-image, let A be a pre-image of one. And we were given that's a good question. Did we use the assumption that G is abelian? I personally don't see where we have used the property that G is abelian. So can you say that's a very good question. Let G be an abelian group. See, we are given there is a surjective group homomorphism from G to Z. So can G be non-abelian? It's a very interesting question,
Yes,
actually.
yes. G becomes abelian.
G becomes abelian because of that. That's a good point.
Z plus
So
is
we have
abelian.
phi from G to Z plus, and suppose G is not abelian. Suppose G is not abelian, and so this implies there exists x comma y in G such that xy is not equal to ix. So this implies phi of no, I didn't think of it. Yeah, sorry. I can't say phi of xy is not equal to phi of yx because we are not given its injective, which we are given its subjective. Anyways, interesting. I didn't think about this. But to answer your question, we haven't used G is abelian as far as my knowledge goes. If someone's able to see where we have used the fact that G is abelian, I'll be happy to look at it. Yeah? Is that okay? Okay. I'll continue with to the next question. No. It's not an inconvenience. It's actually a very good question. It's fine. Yeah. So let M denote the number of injective, which is the 1-1 homomorphisms from Z mod 3Z, which is Z3 to R mod Z, and N denote the number of homomorphisms from R mod Z to Z mod 3Z, then which of the following is true? So R mod Z is basically the quotient group. So R is a group with respect to addition, and Z is a normal subgroup of R with respect to that. So we can do the quotient R mod Z, which is also a well-defined group. So now we are asked about injective group homomorphisms from Z mod 3Z to R mod Z. Interesting. So now let F from R mod Z to Z3 be an injective group homomorphism. So what's something about R mod Z which we know, the group R mod Z? First thing about R mod Z properties. So for every first thing we have is, no, this is the property which we will be using. For every natural number n, there exists a unique element x bar in R mod Z of order n. It's quite surprising. But does this have to be unique? No, it need not be unique. Sorry for that. So basically the thing is, for every n in n, there exists an element of order n in R mod Z. Right? So this is a property of R mod Z which we'll be using here in this question. And basically the element which comes to our mind is 1 by n. Let me just keep this on top. You just take x bar to be 1 by n plus z. It has order n. So this is a group with respect to addition. Remember that. So x bar, n times x bar. So this implies n times x bar is basically n times 1 by n plus z, which is basically 1 plus z. And since 1 belongs to z, this is in fact z. And that's the identity element of R mod Z. Right. So that's the first thing we'll remember. Anyways, coming back to this. F from R mod Z to Z3 is an injective group homomorphism. So, sorry, Z mod 3 is Z3 to R mod Z. Sorry for the confusion. So again, this is cyclic with generator 1 bar. Yeah. So it's again enough to see the images of 1 bar. So first thing, f of 1 bar is not equal to 0 plus z. Why? Because f is injective and 0 bar anyways goes to 0 plus z. F of 1 bar and this is not equal to f of 2 bar. So all these three are distinct elements. That's the injectivity coming in. So this is the first thing. And what's the second thing? 3 times f of 1 bar is 0 plus z. Because f of 1 bar has order 3 in z mod 3z. So 3 times f of 1 bar is this thing. So now let x plus z be f of 1 bar. So now this implies 3 times x plus z is equal to z. So this is basically 3x plus z equals z. This is basically 3x is an integer. Right? So this means x is of the form a by 3, where a is an integer. So from this what we get? X plus Z can only be either 0 plus Z, which is Z itself, 1 by 3 plus Z, 2 by 3 plus Z. What would be the next one? It would be 3 by 3 plus Z. But 3 by 3 is 1 and 1 plus Z is Z because 1 already belongs to Z. Similarly, 4 by 3 plus Z would be 1 by 3 plus Z. 5 by 3 plus Z would be 2 by 3 plus Z. So in fact, these are the only 3 elements which you can get. So now X plus Z can't be Z because we have assumed f of 1 is not Z. Right? So f of 1 can't be Z. So X plus Z can't be Z, which implies either f of 1 bar is equal to 1 by 3 plus Z or f of 1 bar equals 2 by 3 plus Z. So in both these cases of f of 1 bar, you get f is injective. So in this case, you will get 0 bar goes to Z, 1 bar goes to 1 by 3 plus Z, and 2 bar goes to 2 by 3 plus Z. So this gives an injective map. And in this case, you have 0 bar goes to Z, 1 bar goes to 2 by 3 plus Z, and 2 bar goes to 1 by 3 plus Z. So this is basically, these are in fact basically the 2 injective homomorphisms possible from Z3 to R mod Z, which implies MS2. Right? So we have got MS2. Now let's look at N. N denotes the number of homomorphisms from R mod Z to Z mod 3Z. Okay, fine. If from R mod Z to Z mod 3Z is a homomorphism. Nothing else we are given. Injective, surjective, no restraints. So we always have one homomorphism between any two groups, which is the trivial homomorphism, where every element of G goes to the identity of the codomain. So that we always have. So now, and that's called the trivial homomorphism. So we'll take F is non-trivial, which implies there exists X plus Z such that f of X plus Z is not equal to 0 bar. Now this gives us two possibilities. F of X plus Z equals 1 bar or f of X plus Z equals 2 bar. So now if f of X plus Z is 1 bar, what can we say? So in both these cases, we can actually say that 3 times f of X plus Z is basically 0 bar identity, because both of them have order 3 in Z mod 3Z. This implies X is again of the form A by 3 for the main Z. Are we able to go anywhere in this case? So we have specific condition, like if at all it's going to a non-zero element. So basically, what's the condition we have? If f of X plus Z is not equal to 0 bar, then X plus Z is either of the form 1 by 3 plus Z or 2 by 3 plus Z. Right. So we are basically getting, how to put this, a constraint on the way we can work with this. So How do we proceed now? So suppose there exists an x such that so if f of x plus z is non-zero, then x plus z has only two forms. Yeah. So thus you can write 1 by 3 as 1 by 4 plus 1 over 12. Making sense? Yeah. And you can write 2 or 3 as half plus 1/6. Yeah. Right. So we have these two possibilities. So f of 1 by 3 plus z. So we know f is a homomorphism, and if f of x plus z is non-zero, then these are the only two possibilities. Right. This gives us if x plus z is not any of these two, this implies f of x plus z is 0. Right? So now we have 1 by 3 can be written as 1 by 4 plus 1 by 12, and 2 by 3 can be written as 1 by 2 plus 1 by 6. And 1 by 4, 1 by 12, 1 by 2, 1 by 6. All four of these don't have that format, like the format of this thing. So for all four of these, 1, 2, 3, and 4, we'll have f to be 0. So this actually gives us f of 1 by 3 plus z is 0, and f of 2 by 3 plus z is also 0. So basically what we got here is, given any homomorphism f from R mod z to z by z mod 3z, the only possible homomorphism is the trivial homomorphism. Right. So what we did here, just to recap, so we assumed f is a homomorphism, and if everything goes to 0, then that's a trivial homomorphism, that's always counted. And now we suppose there exists something such that it doesn't go to 0. Right. So we were able to show that has a very specific form, which is basically this thing. So we are able to show if x is not of this form, then it always goes to 0. But we were able to show these two elements which were possible to be non-zero. They can also be written as sum of two elements which will have their image to be 0. So their images will also have to be 0. So we basically were able to show somehow that the only possible homomorphism is the trivial homomorphism, which implies n is 1. So this is the question, the answer is m equals 2 and n equals 1. I know it's a very difficult question to prove even during exam. But if what I would suggest always with respect to entrance exams is whenever it has negative marks, only if you are confident with the question, answer it. If it doesn't have negative marks, I think it's worth giving a guess. Right. This question might have had negative mark because it's an MCQ. But yeah. Anyways, moving on to the next question. I don't think I'll be able to complete all the questions today. Anyways, the number of surjective onto group homomorphisms from S4 to Z mod 6Z is equal to. This is again a numerical answer question from GATE. So let's try to do this. Let F from S4 to Z mod 6Z be surjective group homomorphism. So it is surjective. So what can we do if it's surjective? Surjective implies for every element in Z mod 6Z you have a pre-image. And whenever we look at cyclic groups, we always tend to look at its generators. So let sigma in S4 be such that f of sigma equals 1 bar in Z mod 6Z. So since 1 bar has order 6, 1 bar has order 6 in Z mod 6Z. This implies 6 f of sigma is 0 bar. Sorry. Yeah. So let n be order of sigma. Right. Then f of sigma power n is 0 bar. Then f of sigma power n is 0 bar. Why? Because sigma power n is identity, and identity always goes to identity, which is 0 bar. This implies n times f of sigma is equal to 0 bar. This implies n times 1 bar equals 0 bar, which implies 6 divides n. 6 is basically the order of 1 bar. So we have 6 divides n. So now we have n is the order of any element. Sigma is in S4. So we know that the possible orders for any sigma in S4 is basically 1, 2, 3, 4, which we had already seen before here. These are the only possible orders: 4, 3, 2, and 1. Right. This implies n can only be in 1, 2, 3, 4. Right? So this we have, and this we have. Does these both give us a contradiction? You want n to be either 1, 2, 3, or 4. And you also want 6 to divide n. That's not possible. So we get a contradiction. So our assumption here, let this thing is false, which implies the answer is basically 0. Which means there is no surjective group homomorphism from S4 to Z mod 6Z. Okay. So now next question. Which of the following statements are true? Okay. R plus, the first one, this is basically the group of real numbers with respect to addition. R plus comma into is basically the group of positive reals with respect to multiplication. This is R star. Star is basically non-zero reals with multiplication. C star, non-zero complex with multiplication. And Q plus is set of rationals with addition. So out of these four options, one of the options is obvious. Which one? Like it's obvious that that statement is not true. And that doesn't have to do anything with group theory. It's basically D. D is not true. Why? Because if at all they were isomorphic, the first thing we get is a bijection. We'll get that there will be a bijection from R to Q as sets. And as sets R and Q are, there is no bijection between R and Q because Q is countable and R is uncountable. So set theoretically, we can rule out one option, which is R plus is isomorphic to Q plus. But we'll have to work on the other things. Right? So what? So now let's look at some properties. Now let's look at firstly R star and C star. So, sorry, if suppose f from R star to C star is an isomorphism, let x in R star be such that f of x is equal to omega, where omega is basically a primitive third root of unity, 2 pi by 3. Then order of x in R star is basically order of omega and C star because they are isomorphic, and this is 3. So this implies x cube is 1. And x is a real such that x cube is 1. This implies x is 1. This implies omega equals f of x is 1. Why? Because 1 is an identity of R star. So it will map to the identity of C star, which is again 1. This gives us a contradiction. So basically, what was the idea here? X power n equals 1. This. So basically, C star has elements of finite order for every n, which is for every n, there is an element in C star of order n. Whereas that's not true in R star. Right? So this is not true. You can actually use a similar argument to prove that R plus and C star are not isomorphic. Because C star will have any, for any n, so this property of C star with respect to multiplication is that for all n in n, there exists an element in C star of order n. And that's basically primitive roots of unity. Right. And this is precisely e power 2 pi I by n, which is basically the primitive, which is basically one of the primitive nth roots of unity. Right. So similarly, we can have R plus. Yeah. So now what about elements of finite order in R plus? Let x belong to R such that order of x is n, which is finite. R is a group under addition. So x plus so on up to x is 0. 0 is the identity, which implies nx is 0. This and n is any natural number, n greater than equal to 1. This implies x is 0. So the only element of order, of finite order, in R plus is the identity 0. So for any n greater than equal to 2, R plus doesn't have an element of ordering. So what does that give? So basically with these two things, you can actually show that they can't be isomorphic. So now what about the first one? So now one could use, what is it? Competitive exam strategy and say that one is true. Because all the three others are false. So one of them has to be true. However, one can check this. F from R plus to R plus comma multiplication, f of x e power x is an isomorphism. So now, what gives us the idea for this isomorphism? See, you basically want f of x plus y to be f of x into f of y, because the operation in the codomain is multiplication, whereas the operation in the domain is addition. So you need such thing to happen. And that would easily take you to equations of this form. Because only when you multiply in powers like e power x times e power y, that would give you e power x plus y. So whenever you want this kind of solutions, you always look at exponential functions. Right. So now this is another question about basic properties of group homomorphisms in finite groups. Which of the following statements is not true? Image of any subgroup of phi under phi. And image of any subgroup is a subgroup. So now let K be a subgroup. We are asked, is phi of K contained in H a subgroup? Let's try to show it. Let x comma y belong to phi of K. I'm using the single step test, which is basically xy inverse. So I can write x as phi of A, y as phi of B, A comma B in K, and xy inverse is basically phi of A, phi of B inverse, which is basically phi of AB inverse, and this belongs to phi of K because AB inverse belongs to K because K is a subgroup. So phi of K is a subgroup. So first statement is true in general, so we can delete it. For every G in G, order phi of G must divide the order of G. Let G belong to G and M be order of phi of G. This implies phi of G power M is equal to identity in H. This implies phi of G power M equals identity. This implies G power M is in the kernel. But this doesn't give us anything related to divisibility of order of phi of G and order of G. But what we do get is if n is order of G, yeah, if n is the order of G, we have phi of G power n is identity because G power n is identity. This implies phi of G the whole power n is identity. This gives us m divides n. So we have, okay, we did get what we want, sorry. We did get order of phi of G divides the order of G. Sorry, I got confused. So if we take m is the order of phi of g and n is the order of g, we have phi of g power n is e, which means n order of phi of g divides the order of g. So this is actually true in general. So this is not the answer we want. So we already know image of any subgroup is a subgroup of H. G in itself is a subgroup of G. So phi of G will always be a subgroup of H. So C is also not true. C is true in general. So the option remains as D. And I think I leave it for you to find the counterexample. So I think I'll stop here for today. If possible, we can have one more session next week and I can go through the remaining questions. Is that fine, sir?
Yeah, yes. Thank you. Thank you, Adithya.
Yes, sir.
According to your availability of time, we can schedule a next session.
Yeah, sure, sir. So,
Adithya, now you can turn off the presentation so
Yeah.
that we can move to the feedback session.
yes, sir.
Okay, thank you, Adithya, for this nice session with a good collection of previous year questions from different competitive examinations.
Thank you, sir.
So, dear participants, now it is your time to share the feedback. Feel free to share your comments.
Good evening, sir.
Yes, Varada.
Good evening, sir. My name is Varada. So I've completed my BSc from 𝕨𝕬𝕥𝕙 College, and right now I'm like preparing for JAM. So talking about today's class, I really enjoyed the session throughout. As sir said, like all the questions were like very interesting, and you explained everything like from the scratch. So I felt very comfortable listening to the class, and yeah, I think I'm feeling much more confident in the subject right now. So looking forward to more sessions from your side, and thank you
Thank
so
you.
much, sir, for the
Yeah.
wonderful session.
Okay, thank you, Varada. Aditya, can you use the same device for your voice as well?
Which one, sir? This one?
Yeah, video one.
Okay, so just a minute. I think I'll leave with the other
Okay.
one.
Yeah, good. Yes, Dharmendra,
Yeah. Yes, sir.
do you want to share a
I am
feedback? Then please.
from UP, and I am preparing for all these exams, IIT and TFR also. And this session was very nice, and the problem selection also nice from PYQ of TFR and other exams. Also. I want to ask about TFR and CFI preparation because these are little bit advanced and deep knowledge required. So how to prepare for these exams? Because if we solve without any guidance and without any solution, then we cannot solve more problems at home. So what we should do?
Regarding the TAFR exams, um, the thing with TAFR exams is it has a mix of questions which are both like doable and somewhat difficult. Like for example, the first question which I gave today, which I discussed today, which was basically the number of even positive integers such that every group of order n is abelian. That's actually a TAFR question. So TFR does have easy questions in it. I do agree that it's very difficult to do all the questions, but this is my general rule whenever I go for any competitive exam, is that I go through every question first within the first 5 to 10 minutes, and I try to mark the questions which I feel I am comfortable doing first. I don't want to start with questions which will make me uncomfortable or something which I feel might be difficult. Because that can demotivate us quite early in the exam. So
Yes, sir.
one thing which this is something which I try to do for every exam. I'm sorry, I can't particularly answer for TAFR because I am a person who didn't write the TAFR exam because I know it would be difficult. So I didn't
Yeah.
write TAFR exams. So yeah, so one thing which I would suggest is go through the questions first,
Yeah.
and then see which one kind might be doable. And of course, the thing with group theory and algebra related stuff is there will be quite a lot of questions where you might be wanting examples, like at the top of your head. And it's always difficult to do so. Like we can't keep in our mind of all the different group structures possible to go to an exam, because the exam is not just about group theory. There are multiple topics in the exam.
Mm.
So we do try to think of certain examples in mind and go. Like whenever if the question is about non-abelian groups, we try to think of Sn, Tn, or matrix multiplications, cyclic groups, Z mod and Z, or an infinite cyclic group, integers. So these kind of some group structures, it's important for us to remember. And most probably, whenever you are trying to go for counterexamples, in some cases, I think most of the times Sn or some matrix multiplication or these kind of things works. Right. So that's one thing which I can give you about the counterexamples part. And I would always say whenever we have true or false questions, proving true or false is always difficult. You might get an instinct once you look at the question, whether it be true or false. So what would my thing is, what I try to do is, I try to prove it, right? I try to start proving it. Somewhere I might get stuck in between. It's either because my proof, it's either because the statement might be false. That's why I'm not able to prove. If I'm stuck at some part of the proof, I'll have to think, okay, why am I getting stuck here? So with this stuck part, can I get a counterexample to show it's false? Right. So that's one more thing which we can think about true or false statements. When it comes to TFR, TFR has quite a few true or false statements. Yeah.
Yeah. Or how to prepare for interview also for TFR, because I appeared in interview in 2008 or 9 about.
So
I cannot.
yeah, TFR interview, of course, I have no experience in it, but in general for interviews, I think interviews are much more, how to put this, when you have people sitting in front of you for the interview, the first thing they do ask which topics you are comfortable in, and they do try to start off with those topics. And one more thing is whenever we are stuck at some point, the faculty do try to help us most of the times. They might try to give us some hint on, suppose we start doing a problem and we are stuck somewhere. They do give us some help. Like I remember when I gave my ISI PhD interview, I got stuck in a question and they did help me out. Like, trying to move forward in that question. So they are quite helpful when it comes to that. And also when it comes to interviews, I personally feel interviews are much more relaxed in the sense that, I mean, we do all our preparations as we go into the interview. But I think we have to be relaxed during the interview and be as much open as possible in cases when we don't know the answer. I think if there is a question which you don't know, like how to go forward, I think it's really good that we put it out front, like, sir, I'm not able to go forward from here. They might help us at that point. Yeah. So that's it about interviews.
Yeah. Okay. Thanks, sir.
Thank you.
Thank you, Dharmendra.
Thanks, sir.
This-
Thanks, sir.
Sir, good evening, sir.
Yeah.
I am Reshma, pursuing 𝕨𝕚𝕥𝕙 at 𝕨𝕚𝕥𝕙 College, Kannur. I joined here. First, I want to sorry, sir. I joined here a bit late today, so I got only 15 minutes of the class. But those 15 minutes were very useful, and you taught very well, sir. Sir, I feel like I had missed your full session. So thank you, sir. Very clear explanation, and I'm eagerly waiting for the next class, sir. Thank you, sir.
Yeah. Thank you so much. I think even someone has messaged in the chat asking it would be very helpful if we can get another session before the December net exam. Honestly, honestly, sir, if possible, we can have it next week.
Okay.
It might be even before the TFR exam.
Yeah. So
That's
please
useful.
let me know your convenient date so
Yeah.
that we can schedule it.
Yeah, sure, sir. So that we can think about.
Yeah.
Yeah. This weekend I have some work, so that's why weekend was not possible.
Okay.
But
Yeah,
yeah,
we
next
can,
week.
yeah, we can go for working days. The evening time
Yeah.
is, I think, comfortable for many participants.
Yeah. Sure, sir. Yeah, we can look into that. Yeah.
So,
Hello,
yeah,
sir.
yeah, it's Neha.
Yeah. And hello, Adithya Bhaiya. I am Sneha, and I have completed MSc from ICDVM. So
I do remember.
maybe, yeah, but I have met you there.
Yeah.
So
Yes, Neha is your
currently,
junior. Yeah.
Yeah, I do remember, sir. Yeah.
so yes, now I am preparing for GATE and NEET exam,
Okay.
and the station is very nice. You have explained every question in detail. I have attended all the sessions, but sometimes there was some network problems, so I got disconnected. So I was not active participant today, but the session was really nice. So I am eagerly waiting for the next session also.
Yeah. Thank you. Thank you so much.
Thank you, Sneha. Yeah, Archana.
Hello, sir. Sir, due to my net issues, I'm not able to switch on my video. I really enjoyed this session. It was really nice.
Okay, so dear participants, yeah, the points mentioned by Adithya as an answer to the query of Dharmendra was really important. While attempting a competitive examination, you should start with the questions that you are really 100% confident. Otherwise, you will lose your mind from the very beginning, and it may have a very negative impact on your performance. So that's a very important point. And also the points he mentioned about the interview, that is also very important. So I'm sure that our participants will clearly note that points and make use of it. So if any of you would like to make any comments, then you can do, otherwise we can wind up the session now. Okay. So once again, thank you, Adithya, for this session. Thank you for your support in Math Aspirants, as you are actually a member of our group from your very PG times itself. So it is my pleasure and privilege that you are having as a resource person in our platform.
Yeah.
Makes me very happy.
Yeah. Thank you, sir. Thank you so much for the opportunity. We'll hopefully meet soon.
Okay. So
Yeah.
Adithya, it will be good if you can share the PDF of today's session.
Yes, sir, sure, sir. I'll share it with you.
Okay.
Yeah.
Yeah. Okay, so let us wind up here. Thank you. Thank you, everyone.
Thank you so much, sir. See you. Yeah.
Thank you. Bye.
Yeah. Yeah. So research experience, honestly, I'm in my second year of PhD and I haven't started much research. So maybe
On
2,
a
3 years
later
down the line,
occasion,
I can,
on a later occasion, we can explain.
yeah, maybe 2, 3 years later, I can tell what research
Yeah.
experience is.
Yes.
Yeah. Anyways, thank you so much, sir.
Okay, yeah, let us wind up here. Good night.
Yeah.
Thank you.
Thanks, sir. Bye, sir. Bye, sir. Good night.
Good night.